Good day to you, sir. Today we will be reporting on experiment 17. The topic is acids and bases. Let's get right into it. For our introduction, acids and bases are essential substances used in laboratories, industries, and many household products. They play important roles in biological processes, food preparation, cleaning, and environmental systems. This experiment that we're reporting on is focused on identifying the properties of acids, the properties of bases, and observing the reactions with indicators and metals and determining whether common household materials were basic or acidic. So, for the properties of acids, they neutralize bases, they turn blue litmus paper red, and they have a sour taste. They also react with active metals to release hydrogen gas. Examples are hydrochloric acid, sulfuric acid, acetic acid, and phosphoric acid. For the properties of bases, they neutralize acids, they have a slippery or a soapy feel, they turn red litmus paper blue, and they have a bitter taste. Examples are sodium hydroxide, calcium hydroxide, ammonium hydroxide, and potassium hydroxide. One important thing to note also about acids and bases is that anything acidic is anything with a pH below 7, and anything basic is anything with a pH greater than 7. If it's just 7 by itself, it's considered neutral. So for the household acids and bases, these are also the substances used for the experiment. So for common acidic household substances, we have vinegar, which contains acetic acid, aspirin, which contains acetyl salicylic acid, powdered juice, which contains citric acid, and that's it. For common basic household substances, we have baking powder, which produces sodium bicarbonate, milk of magnesia, which contains magnesium hydroxide, detergent, which contains basic surfactants. We have shampoo, which contains ammonium compounds, and we have cuticle remover, which contains strong bases like sodium hydroxide or potassium hydroxide. We have spirit of ammonia, which contains ammonium hydroxide, and we have lime water or apog, which contains calcium hydroxide, a solution of calcium hydroxide. Next, my group mate will take it on from here. Thank you very much.
So now, let's move on to the expected results of this experiment. So first, let's start with acid. So for acids, we expect that for the first litmus test, the blue litmus paper will turn into red. And for the reaction with phenolphthalein, it will remain colorless. And for the reaction with methyl orange, it will turn red. And for reaction with magnesium ribbon, there will be a vigorous reaction with bubbles of hydrogen gas. And for reaction with copper shavings, there will be little to no reaction, except stronger acids may react slowly. Next is for bases. So for the reaction with litmus paper, the red litmus paper will turn into blue. And for the reaction with phenolphthalein, it will turn pink. And for the reaction with methyl orange, it will turn yellow. And for reaction, lastly, with magnesium ribbon and copper shavings, there will be little to no reaction, since most metals do not react with bases except aluminum and zinc. So now, let's talk about theoretical results. So we will tackle 3 theoretical results. First, we have the acids, results for acids, results for bases, and then results for household acids and bases. So here we have the table for the results of an experiment with acids. So for the first column, we have the properties, different properties or different reactions, which is the litmus paper, phenolphthalein, methyl orange, magnesium ribbon, and copper shavings. For the next columns, we have the different acids and the results. So the first acid we have is hydrochloric acid, sulfuric acid, phosphoric acid, and then acetic acid. So for the first reaction, acid litmus paper. So it's basically just the same for all acids. The litmus paper, the blue litmus paper turned into red. So next is the reaction with phenolphthalein. So it's just the same for all acids. It remained colorless. And for the methyl orange, it turned into red, which is just the same for all acids. And for the reaction with magnesium ribbon in hydrochloric acid and sulfuric acid, there is a rapid bubbling. For phosphoric acid, there's moderate bubbling, and for acetic acid, there's slow or weak bubbling. Lastly, we have the reaction with copper shavings, and for all acids, there is no reaction. So that's it for acids. Let's now move on to bases. So same with acids, we have for the first column the properties, the different reactions, which is the litmus paper, phenolphthalein, methyl orange, magnesium ribbon, and copper shavings. So for the next columns, we have different bases, namely sodium hydroxide, potassium hydroxide, calcium hydroxide, and then ammonium hydroxide. So for the reaction with litmus paper, it's just the same for all acids. The red litmus paper turned into blue. Next is the reaction with phenolphthalein. So in sodium hydroxide and potassium hydroxide, it turned into pink. While in calcium hydroxide, it's light pink. And for ammonium hydroxide, it's a faint pink. So next is the methyl orange, reaction with methyl orange. So it's just the same for all bases. It turned into yellow. And lastly, for the magnesium ribbon and then copper shavings, for all bases, there is no reaction. So that's it for the bases. So let's now move on to the next result, household acids and bases. So for the first column, we have household substances, different household substances or acids or bases. And for the next columns are its properties, mainly the color, odor, its color with phenolphthalein, reaction with litmus paper, and the name of the acid or base that is present in the substance. So we will talk about each substances and its properties one by one. So to start, vinegar. Its color is clear and it has a strong smell. When reacting with phenolphthalein, it is colorless. And in reaction with litmus paper, the blue litmus paper turns into red, and the name of the acid that is present is acetic acid. Next is the baking powder. It is a white powder which has a strong smell, and when reacting with phenolphthalein, it becomes pink, and with litmus paper, the red litmus paper turns into blue, and it has sodium bicarbonate, which is a base. And then milk of magnesia. It is a white suspension in color, it is odorless, and when reacting with phenolphthalein, it is a strong pink. And when reacting with litmus paper, it's just the same with the bases. It turns red litmus paper into blue and has magnesium hydroxide as a base. And then aspirin, it is clear or slightly cloudy with slightly medicinal odor, and when reacting with phenolphthalein, it is colorless, and then when reacting with litmus paper, it turns blue litmus paper into red and has acetosalicylic acid. And then antacid, it is cloudy or slightly white with no strong odor. When reacting with phenolphthalein, it becomes pink, and in reaction with litmus paper, it turns red litmus paper into blue, and it has calcium carbonate or magnesium hydroxide, so this is a base. And the next, detergent, it's colored or a clear liquid, it depends, and then it has a soapy smell. And then, when reacting with phenolphthalein, it becomes pink, and in reaction with litmus paper, turns red litmus paper into blue and has sodium carbonate or sodium hydroxide, so this is again a base. Then the next one, we have shampoo, which is clear and fragrant. When reacting with phenolphthalein, it becomes slightly pink, and it turns red litmus paper into blue, and it has ammonium compounds. Next, cuticle remover. It is clear and has a slight chemical smell. When reacting with phenolphthalein, it becomes strong pink and turns red litmus paper into blue and has potassium hydroxide, so this is a base. The next is lime water, which is clear, odorless, and when reacting with phenolphthalein, it becomes pink and it turns red litmus paper into blue and has calcium hydroxide, again a base. and then spirit of ammonia, which is clear and has a strong pungent smell. And when reacting with phenolphthalein, it becomes strong pink, and it turns red litmus paper into blue and has ammonia, which is a base. And then powdered juice, it is colored, has a fruity smell, and when reacting with phenolphthalein, it becomes colorless, and it turns blue litmus paper into red and has citric acid or ascorbic acid, which is basically an acid. So to conclude everything, Experiment 17 showed the main differences between acids and bases using the test litmus, phenolphthalein, methyl orange, and methyl reactions. It also revealed that many everyday products at home contained acids or bases. So now, let's move on to Experiment 19, which is the methods of purification of organic compounds. So to start, in organic chemistry, the products we obtain from reactions are rarely completely pure. They often contain impurities such as leftover reactants, byproducts, or substances formed from side reactions. These unwanted materials may mix with the product or be absorbed by it, affecting its quality. Because of this, purification is an important step to ensure we obtain a pure compound, especially when performing accurate tests or identifying elements in organic substances. So in this experiment, we have different methods of purification of organic compounds, which are mainly crystallization, distillation, extraction and chromatography, sublimation, dialysis, decolorization, and formation of addition compounds. So we will talk about it one by one, but first, let's start with crystallization.
What is crystallization? Crystallization is the process of forming solid crystals from a solution as the solid comes out in an ordered, pure solid form. Slow crystallization allows only the correct molecules to fit into the crystal lattice, giving larger, purer crystals with fewer trapped impurities. How can we obtain smaller and purer crystals? So we use a more concentrated hot solution and cool it slowly with gentle stirring, and then scratch the glass or add a seed crystal to control nucleation. What is recrystallization? Recrystallization is the purification of a solid by dissolving it in a hot solvent and then allowing it to crystallize again so that impurities stay in the mother liquor. Why should solutions not be filtered rapidly? Rapid filtration can cause premature cooling and crystallization on the filter, trapping impurities and lowering yield in purity. So the expected results: hot crystallization of crude oxalic acid. So the crude oxalic acid fully dissolves when heated. When the hot filtrate is cooled in ice water, white needle-like crystals begin to form. The crystals appear more uniform, purer, and larger than the crude sample. The residue or impurities remain in the filter paper and do not crystallize. Crystallization at low temperature. Impure benzene placed in an ice salt bath forms white solid crystals around the inside of the tube. Liquid impurities remain separated as an oily layer, and the crystals appear clear and transparent when pure, cloudy when slightly impure. Distillation is a purification method in which a liquid is vaporized and then condensed back to liquid, separating it from less volatile components. So why is acetone purified in this process? Acetone has a lower boiling point, 56 degrees Celsius, than water, so it vaporizes first and can be collected as a relatively pure distillate, leaving most water behind. For the expected results, distillation of acetone as the mixture is heated. Acetone's boiling point is 56 degrees Celsius, begins to boil first, so vapor rises through the side arm and condenses in the condenser. The distillate collected first is clear, colorless acetone-rich liquid. The temperature stays around 56 degrees during early distillation, the acetone fraction. So after most acetone is removed, the temperature rises toward 100 degrees Celsius and water begins to distill. Appearance of distillate. So first fraction, acetone-rich fast evaporation and strong acetone odor. And for the last fraction, mostly water, slower evaporation, and minimal odor.
Extraction and chromatography, which is used to separate plant pigments from leaves. What is extraction? Extraction is a method that uses a solvent to separate substance from a mixture based on their solubility. Color of the extract. So what is color of the extract? The extract is usually green because chlorophyll sometimes it looks yellowish or yellow tint due to the other pigments like carotenoids. What happened to the pigment injected on a chalk when immersed in the breaker with petroleum ether? When placed in a petroleum ether, the pigments move upward with the solvent. They separate because each pigment had a different polarity. The pigments seem were carotenes, xanthophyll, chlorophyll A, and chlorophyll B. They move different distance on a paper. Results: several colored bands appear on the filter paper. Each band corresponds to the different plant pigment. The distance traveled by each pigment show how strongly it interacts with the other solvent. Conclusion: plant pigments were successfully extracted and separated. Chromatography revealed multiple pigments present in the leaves. The experiments show how solvent interaction and polarity determine the movement and substance on chromatographic paper.
Sublimation. The theoretical explanation for sublimation is the phase changes where a solid turns directly into gas without passing through the liquid phase. Only certain substances can sublimate. Example, naphthalene, iodine, and dry ice. Sublimation used to separate volatile solids from non-volatile impurities. So this is the setup for sublimation. So the expected result is upon heating naphthalene should vaporize. Vaporizes, cools, and deposits as white crystalline solid on the funnel or filter paper. Filter paper should show white crystals. And for the actual results, naphthalene form visible crystals on the filter paper. Crystals appeared white and flakes-like, matching expected sublimation behavior. No liquid phase observed confirms sublimation. And for the sublimation, lab questions are: first, define sublimation. Sublimation is the process where a solid changes directly into gas without passing to the liquid state. And the second question is, what is the sublimated substance? The sublimated substance is naphthalene, which deposited as white crystal on a filter paper. And for conclusion, sublimation was successfully demonstrated as naphthalene changed from solid, vapor, solid to solid, depositing white crystal on the filter paper. Dialysis. So the theoretical explanation for dialysis is the movement of small particles through the semi-permeable membrane, leaving large molecule trapped. So small molecule can pass through and large molecule cannot pass through. Egg membrane act as the semi-permeable membrane. So this is the setup for dialysis. And the expected result, after 30 minutes, distilled water outside the egg should contain chloride ions, expected to diffuse, no starch too large to pass. And for the test, iodine test, starch is present. Violet means positive. And for the silver nitrate test, chloride is present. White, precipitate means positive. And for the actual result, for silver nitrate test, the result is white turbid, and the interpretation is chloride ion diffused out of the egg, NaCl passed through the membrane. And for the iodine test, the result is golden brown, interpretation is starch did not pass through the membrane. This confirms the selective permeability of the egg membrane. So, dialysis questions. The first question is, define dialysis.
Dialysis is the separation of small particles from the large particles through a semi-permeable membrane that allows only small molecule to pass. So second question, what does the result indicate after treating dialysate with silver nitrate? So the solution turned white turbid, indicating chloride ion are present in the dialysate. So NaCl diffused through the egg membrane. So the third question is, after adding iodine solution to the dialysate, what does the result show? So the solution turned golden brown, indicating starch is absent. Starch did not diffuse through the membrane. Conclusion, dialysis shows selective permeability. So, sodium chloride is a small molecule that passed through the egg membrane, and the starch is the large molecule that cannot pass through to the egg membrane.
Colorization. Decolorization is a method of removing brightly colored organic impurities from a sample mixture. This is to get rid of unwanted color substances in a mixture. In the procedure, it is called the decolorization of brown sugar. First, we pour 30 ml of brown sugar solution and bone black, then boil it for 15 to 20 minutes. It is usually carried out in the solution phase after the solid product and impurities are dissolved in a suitable solvent. By using bone black as an adsorbent which attracts and holds the colored substances, leaving the brown sugar solution clearer and more purified. In expected results, boiling the brown sugar solution with 5 grams of bone black improves the process by allowing better contact between the bone black and the colored impurities, resulting in more effective decolorization. The bone black acts as an adsorbent, removing the colored substances from the solution. These impurities cling to the surface of the bone black, leaving the solution clearer and lighter in color. So how was decolorization accomplished? It was accomplished by adding the 5 grams of bone black to the brown sugar solution and boiling it. The colored impurities in the solution attached to the surface of the bone black through a process called adsorption. After boiling, the mixture was filtered through a funnel with filter paper, removing the bone black along with the absorbed impurities, leaving a water-like solution filtrate. Differentiate adsorption from absorption. In adsorption, a substance attaches only to the surface of another material, just like how bone black removes color from a sugar solution. Meanwhile, absorption occurs when a substance penetrates and spreads throughout the material, such as water being soaked up by a sponge. Absorption is in attaching only to the surface of another material, like how the impurities stuck to the surface of the bone black while the sugar stayed dissolved. Since sugar is not attracted to the bone black has a surface that selectively absorbs the colored impurities, not sugar molecules. Meanwhile, absorption, on the other hand, occurs when a substance spreads throughout another material. So in conclusion, the experiment was a success and it was all expected. The results are achieved. The experiment demonstrates how adsorption can be effectively used to purify solution by removing colored organic impurities, making the solution clearer and successful decolorization process.
Define addition compounds. So addition compounds are the temporary combination of two substances that stick together through weak forces, but not a real chemical bonds. So next. So why does naphthalene sublimate during the process of decomposition of the addition compounds? So naphthalene sublimates because it has a weak intermolecular forces. So it only requires low heat to go directly from solid to vapor, which causes sublimation. And next, what is the role of picric acid in the formation of naphthalene? So sorry, this is naphthalene. The role of picric acid will act as an electron acceptor. So its nitro groups will make electron deficient, allowing it to form a change transfer addition compound with electron-rich naphthalene. And next, why do we need to heat gently with only small flame? So heating it gently will ensure controlled decomposition and proper naphthalene sublimation. So overheating it can destroy the crystals or decompose the picric acid. So let's go to the expected result of these experiments. So cooling the hot naphthalene picric acid solution produced yellow to orange needle-like crystals, which shows the formation of addition compound. So when gently heated, the yellow crystals faded and decomposed, while the crystals of naphthalene appeared on the crucible cover, which confirms sublimation, while picric acid will remain as the residue. So to conclude this experiment, naphthalene and picric acid formed yellow crystals that broke down when heated. So naphthalene sublimate as white crystals on the crucible cover, proving that the addition compound was held by a weak forces, and easily decomposed. So this is the formation of the addition compounds. Thank you.